The next part of Chapter 7 will look at polynomials, dividing them, remainders, factoring, zeros, all of these concepts that you're going to find is intertwined when talking about polynomials. So here we're dividing, and we want the answer written a specific way. We want the polynomial equal to the divisor times the quotient plus the remainder. So the thing I'm dividing by is x plus 1 quantity squared. In order to do this division, I need to expand that to be x squared plus 2x plus 1. The polynomial is x to the fourth, but I need to write out all of the terms all the way down to the constant. And the process we're going to use for long division is what times x squared gives me x to the fourth. Well, that times x squared. And I'm going to multiply back times everything in the divisor. So I'm going to do x squared times x squared. I'm going to do x squared times 2x. And I'm going to do x squared times 1. And then we're going to subtract. The first term better cancel out. I get negative 2x cubed minus x squared, and I'm going to bring the next term down. And I'm going to repeat the process now. X squared times what will give me negative 2x cubed times negative 2x will. And I'm going to multiply that back by all three of these terms in the divisor. And again, subtract. And you got to be very careful with this subtraction step because of negatives. Subtracting negatives, you got to make sure you're subtracting all of the terms. For instance, this term becomes plus 2x. I'm going to drop the constant down, so plus 0, and repeat the process. X squared times 3 gives me 3x squared, and I'm multiplying back. Plus 6x plus 3. And again, subtract. And since there's nothing left to bring down over here at the end, that negative 4x minus 3 is the remainder. And what we could do is say that this division is equal to x squared minus 2x plus 3 plus the remainder over what we were dividing by. But the problem wanted this written a little bit differently. They wanted me to say, okay, x to the fourth, that's equal to x squared minus 2x plus 3 times x plus 1 squared minus 4x plus 3. I factored the negative out of the remainder. Now, if there wouldn't have been a remainder, we could have said that x plus 1, or likewise x squared plus 2x plus 1, was a factor of x to the fourth. But since there's a remainder, it is not a factor. And generalizing that, if x minus alpha, if that linear polynomial is a factor, then there exists some other polynomial such that our factor times the polynomial equals the original without a remainder. So, just to expand on this a little bit, we have this idea that x minus alpha is a factor. We also have talked that alpha is a 0. And just a second ago we said if x minus alpha is a factor, that means that there's no remainder. And if alpha is a 0, that means that our polynomial evaluated at alpha has to equal 0. So all three of these things, or all four of these things, represent the same idea. Factoring, zeros, remainders, they're all intertwined. So here we want to factorize this quadratic. And, you know, with this one, it's not immediately factorable. We don't know what two numbers multiply. There is no real numbers that multiply to 9 and add to give me 4. But what we can do is, if we, looking back to that previous slide, if we can find out what makes this equal to 0, we'll know the zeros, we then know the factors. And I'm going to use completing the square. If we complete this square, we find that x is equal to -2 plus or minus I square root of 5. Or you could have used the quadratic formula to get here also. But the factorization is just going to be x minus those zeros. And here we have this previously unfactorable quadratic factored in its entirety down to two linear factors. In this next problem, we're told what two factors are, and then it says we want to find A and we'll find B, and we want to know what the complete factorization is going to be. Can we factor this down all the way? And for that matter, can we find the zeros? Well, we know that if 2x plus 3 is a factor, that's going to mean that zeros will be x equals two things. X equals 1 and x equals -3/2. We know that. And we know that if these two things are factors, then we should be able to multiply them together and form some quadratic that we can multiply by something else to get to p of x. Well, 2x plus 3 times x minus 1, that's the same thing as 2x squared plus x minus 3. That's what we get when we FOIL out those two. Now the question is, what other quadratic do we have to multiply by here? And what we can do is we can get an idea of that by looking at the terms at the beginning and the end. The highest degree term, 2x to the 4th, well, if I'm going to get 2x to the 4th, it's going to happen by multiplying those two spots. And since I already have the 2, all I need is x squared there. 2x squared times x squared is 2x to the 4th. If I'm going to get this plus 3 at the end, that's going to happen by multiplying -3 by some constant. And that constant needs to be -1. But this middle term, the x term, that gets a little bit trickier. Not too bad, but we got to do a little bit of work to figure it out. So for now, I'm just going to call it bx. And what we can do is we can use the idea of equating coefficients here. I'm going to look at the x terms. I'll start with the x squared terms because that's one I know. And I always like to keep track of what it is that I'm doing. So for the x squareds, well, we're going to get x squared by multiplying those two terms together, those two terms together, and those two terms together. So -2x squared plus bx squared minus 3x squared, that has to equal the total number of x squareds I have. And really, for simplicity's sake, these x squareds here, because all of the terms have them. All we're doing is equating the coefficients. So we can solve this for b. We find that to find, I probably shouldn't have used b since b was up here already. I probably, to be safe, should have called it c or h or some other variable. We'll change this to a c and just pretend that we had that all along. But now I need a and b. So I'm going to need to look at the x cubed coefficients. And I'm going to need to look at the x coefficients. I know that for the x coefficients, they're going to need to equal b of them. And the way we get x coefficients is by multiplying the x times the negative 1 and the negative 3 times the 2x. So this b is going to equal negative 6 for multiplying negative 3 times 2x and negative 1x. So b is negative 7. The x cubed coefficients, well, those are going to have to total up to a of them. And we're going to get x cubed by multiplying the x squared term times the x term. So those guys there. We've got 4 x cubes, and we have 1 x cubed that we're adding together. So a is equal to 5. So I have a and b. I know that my last factor, my last quadratic factor, is x squared plus 2x minus 1. That's not factorable under the real numbers. There is no real number combination that multiplies to be negative 1 and adds to give us 2. We could factor this down to linear factors by finding the zeros of that with the quadratic formula or completing the square, but I'm just going to leave it here for now. The factorized form of this, just to write it in more of a finished fashion, 2x to the 4th plus 5x cubed minus 3x squared minus 7x plus 3, that equals 2x plus 3 times x minus 1 times x squared plus 2x minus 1. If it would have said to find the other linear factors, then we would have to keep going for sure. Two ways to go here. One, we could start out by writing that x minus 2 times a quadratic equals that, or we can use a slightly different idea. We know that since x minus 2 is a factor, that means that x equals 2 is a 0. Which means that when I plug in 2 to this, if I plug 2 into p of x, I better get 0 at the end. So 8 plus 4k minus 6 plus 6, that better equal 0. That's p of 2. So 8 plus 4k, when does that equal 0? That equals 0 when k is negative 2. Or we could have used an idea called synthetic division, or synthetic substitution, it's also called. What we do is we write down the coefficients of our polynomial. So 1k, negative 3, 6. Now we're going to write down the value that makes the linear factor equal to 0. Well, that would be a 2. We're going to drop the first number down, and the rule is multiply on the outside, add on the inside. 2 times 1 is 2. I'm going to put that in the next column. Inside the box, and now I add. Now I'm outside the box again, so I'm going to multiply 2 times 2k, 2 plus k. I'm back inside, so I add. And then I multiply. And this last number is the remainder. And if this is a 0, if 2 is a 0, if x minus 2 is a factor, that remainder better become 0. And I could solve and find that k is equal to 2 again. So what I now know is I know k, that's nice. I know that k is negative 2. So x cubed minus 2x squared minus 3x plus 6, that's going to equal x minus 2 times some quadratic factor. And I know it's going to have to be x squared and a minus 3 in order to get the x cubed and the plus 6. The question becomes, what is the missing term? What goes inside here? How many x's do I need? So I'll call it b times x. I'm going to equate coefficients. Start with the x squareds. The x squared coefficients are going to come from here and there. The x squared coefficients are going to be b plus b minus 2 equals has to equal negative 2. Right there. So we find that b is 0. And we could check that by equating the x coefficients. We'll get the same thing. But what I've got this broken down to now is that x minus 2 times x squared minus 3 is going to equal our p of x. And fully factorizing it to linear factors, this quadratic one is essentially a difference of squares. It's just not the difference of squares we're used to. It's a difference of two irrational squares. So there is our fully factorized polynomial. Now we have information, and we're going to write the equation for this. We have a cubic 3 factors that's cutting the x-axis 3 times. Cool, we know we have 3 real zeros. And those zeros correspond with specific factors. What we now have to figure out is we have to figure out a. And we can do that with the help of this point. We can plug in negative 40 for y and 1 in for x. We get 10a is equal to negative 40. A is equal to negative 4. And this doesn't specify any specific way to write the equation, so I'm just going to leave it in its factored form. And there we have it. The next example, we're given a graph as opposed to written information, but we have the same general idea. We're looking for x-intercepts, and there appear to be three. However, one of them is what we call a double root. You might remember that from the quadratic section. So we can write this as y equals x plus 1 squared, because it hits the x-axis and bounces off again, and then x plus 3, x minus 3, and we can't forget about our friend the a out in front. And we know a point on the graph as the y-intercept. X is 0, y is negative 3. So I plug in negative 3 for y, 0 for x. We find that a is equal to 1/3. So my equation for this fourth degree polynomial is y equals 1/3 x plus 1 quantity squared times x plus 3 times x minus 3. Now we want to find all the roots here. We're not given any information, we're just told the equation. One place to start with this, well, we can start with our graphing calculator. We can go to y equals, we can punch in that function, and we can look at the graph. And I zoomed in just a little bit, and I see that the 0, there's a 0 for this between 0 and 1, closer, or 0 and negative 1, closer to 0. Now I want to know what that is. So just as a refresher, we're going to hit second and then trace. That takes me to the calculate menu. Choice 2 finds me the zeros. I want a left bound. I want the cursor moved to the left hand side, horizontally speaking, of the 0. I want it over here. I've got that here. I hit enter. Now it says right bound. I move it to the right hand side, push enter, press enter to make a guess, and I get a 0 of x equals negative 0.166666 repeating. That repeating decimal is equivalent to negative 1/6. And that's a pretty important thing to know. Since that's a 0, I know that 6x plus 1 is a factor. That's a linear factor that would give me that 0. And I'm going to use synthetic division here. 6, 13, 23. I could have equated coefficients. That works just fine here also. Synthetic division will work also. I'm just trying to show you another way to do it. So we bring the 6 down, multiply outside, add inside. So negative 1 goes up, we add to get 12. Negative 2 goes up, we add to get 18. Negative 3 goes up, and we better end up with 0 because we know that negative 1/6 is a 0. And what we now know is we now have the coefficients of a depressed polynomial. By dividing by 6x plus 1, the x cubed becomes x squared. So this is really 6x squared plus 12x plus 18 with no remainder. And I can pull a 6 out of there. And I'm trying to find all the roots. I want to know what makes this quadratic equal to 0. X squared plus 2x plus 3. Gosh, it'd be nice if that factors, but it doesn't. So we use quadratic formula, or what I would probably use here would be completing the square. Magic number is 1. X ends up being -1 plus or minus I square root of 2. And here we have 3 roots for this cubic polynomial. And if you notice the graph, it only crosses the x-axis once. The last example, I have a complex 0 of this polynomial. I don't know the coefficient of x cubed or x. I want to know what it is. And I also want to know what the other 2 zeros are. And one of them is pretty easy because we know that complex zeros always have to come in pairs. So I know that a second 0 is -3 minus I. And previous section we looked at a property of quadratics that for their sum and product, there's always a nice pattern for those. The sum of 2 roots was -b over a. The product of 2 zeros for a quadratic is c over a. Well, if I add these 2 zeros together, I'm going to get -6. If I were to FOIL these 2 roots together, I would get 10. What this tells me is that the quadratic that gave me those 2 zeros had an a value, a leading coefficient of 1. Coefficient of x would have to be 6, and a coefficient or a constant would be 10. So I know that p of x can be written as some linear factor times x squared plus 6x plus 10. Now let's start looking at coefficients here. I have a total of ax cubed. What times x squared gives me ax cubed? Well, times ax. I have a constant of -30. What times 10 gives me -30? -3. And from here we can equate the coefficients. I'm going to go with the x squared one, x squared coefficients. I have -3 plus 6a equals 9. Going with those 2 terms and those 2 terms. And it has to equal this 9 right there. We can solve this and find that a is equal to 2. I could have done it with the x coefficients. Our coefficients there are -18 plus 10a. That has to equal a. Solve this for a, we get a equals 2 again. So we have 2 zeros, that's nice. We found a, we just need that third 0, and well, it's a nice linear factor. 2a minus 3 equals 0. A is x is 3/2. There's my third and final 0.